Today we are looking at a very simple component in digital electronics, which is a flip-flop. Perfect. So we have a flip-flop. So flip-flop in digital system is, let's call it a memory component that stores binary values of either 0 or 1. So your flip-flop can store 0 or 1. So it's able to maintain two stable states. And for that reason, it's evident that it's a stable element. Perfect. Now, when you have this flip-flop, right? So you have this flip-flop. So a flip-flop, the symbol for the D flip-flop is this one. Well, there are many types of flip-flops, but let's do the D flip-flop, Q and Q bar. So these are the inputs, these are the output. That is the clock signal, that's the clock, that's the output, and then that's the inverse of that one. Well, let's look at first of all the very crucial component here. Now, assuming you are thinking about your phone or your iPad or your laptop. So your phone or your laptop should be running a specific frequency, 100 megahertz, right? So 100 megahertz frequency. Now, when you have that, what does it actually mean for your system to be operating on 100 megahertz? So it tells you the number of occurrences of repeating events per unit time. So they are repeating themselves per unit time. Now, the frequency is actually measured in hertz. So when you have this, it tells you it's close to 100 million hertz. So what it means for your system is that it's taking the clock. And again, don't think about the wall clock. It's the signal. So the clock is moving up and down, right? So the clock is making 100 million ticks per second. Ooh, that seems a lot. But you can imagine this is just 100 megahertz clock. Think about your laptop, which is running at 4 gigahertz. That's the good number of ticking. So let's assume you have this 100 megahertz clock. Now from here, you can find something called the T, or the period. Now period is equals to 1 divided by the frequency. So when you say 1 divided by that, it should give you 10 nanoseconds. So what 10 nanoseconds means is that it takes 10 nanoseconds for your clock in your system to complete one oscillation, which is interesting. So here you'll have the clock signal, and I'm not so accurate, but I'll try to make these so close together. Right, so this is the rising edge, that's the falling edge of the clock, that's the rising edge. And let's make another up and down. That's falling, that's rising, that's falling, that's rising, that's falling, that's rising. Now, we have come up with one thing called the period, right? So it's the time it takes to complete one oscillation. So you have your period be 10 nanoseconds. That's what it means. Now from here to here, so when you have your system having a duty cycle of 50%, right? Duty cycle of 50%. So it means the rising portion of this period is equal to the falling portion of this period. So you have a duty cycle of 40%. At times you might have a duty cycle of 80 to 20, depending, but let's assume everything is equal for this case. Now we have this clock. Now this clock is a clock that is going to be input. This is the clock signal going to that D flip-flop. It's so important because the D flip-flop will not operate without this clock. Now the next thing for the input is the D. Now before doing anything right here, let me bring on something called constraints. Now constraints are kind of the rules of the game. If you violate this one and you're designing a chip, your chip will not function. So the first one is the setup time. The second one, or the first one is setup, and then the second one is the hold time. Now, what means by setup time is that the clock has to remain stable before the edge of the clock. Sorry, I mixed. The data signal has to remain stable before the edge of the clock. So this is the data signal, right? Now, this is the edge of the clock. So it has to remain stable before the edge of the clock. That is the setup time. Now, the clock has to remain stable after the rising edge of the clock. That becomes the hold time. So this is the setup time, and that's the hold time. What it means is that, well, I should have done here. So there's the T setup, and then there is the T hold. What it means that if your data has to remain logic 0, let it be logic 0. If it has to go logic 1, let's be logic 1. Now, at this point, let's make it logic 0, right? So the data is stable, it's at 0. Now, before that, because let's assume, first of all, we are dealing with positive edge triggered flip-flop. Positive edge triggered flip-flop means, data is captured at the rising edge of the clock. Now, this is the rising edge. Now, the next rising edge, data again has to be stable, and then you must have the same setup and hold time, right? Now, at that point, let's bring this data to 0, and then let's move it to 1. Oh, now I almost did some violation. So we move it to 1, and then we move it to 0, and then that's it. So you can continue your signal as far as you want. So what do we want from here? What do we want from here is that we need the Q, and then we need the Q bar. Now, for the D flip-flop, right, we did say Q follows D at the edge of the clock. So at the edge of the clock, Q is equals to D. Now, at this point, we are looking for Q. What's the edge of the clock here? Now, what's the value of D at that edge of the clock? It's 0. So Q stays at 0. Now, let's look at this edge of the clock again. What's the value of D at that point? It's 1. So it moves from there, from 0, it moves all the way to 1. Now, let's look at this point again, right? What's the value of D at that point? It's 0. So it has to move from 1 to 0. And then it goes. What's the value of D at that point? It's a 1. So it has to move to 1. And then what's the value of D at this point? It's a 0. So it has to come down. Easy. So what you have noticed is that there are some changes only on this Q during this rising edge of the clock. Now, for Q bar is the opposite of Q. Actually, it's never asked it, but let's have it. So at this point, it's moving from 0 to 1. So because it's opposite, we'll maintain at 0. Now, at this point, it's moving from 1 to 0. So let's move from 0 to 1 because it's opposite. Now, at this point, it's moving from 0 to 1. So at that point, it should come down. Now, at this point, it's moving from 1 to 0. So at this point, let's move it to 0 to 1. And that's it. So that's basically what your positive edge triggered flip-flop timing diagram will look like. Should be easy to do that. Now let's do continuation because we are using the same data to get the values of well, I'm forgetting something. So setup time is not necessary anymore because we have used in determining the data. So we have used setup time to make sure we meet that condition on this signal. So this one, what is now necessary is the clock. So that's the rising edge of the clock. Let's use the pencil. All right, and that's the falling edge of the clock. Well, not so accurate, but let's use the pen right here. Now, next one, let's use this pencil. Well, you can see that they're not uniform, but we're just using for it as an example. That's the folding edge. Oh, let's use this. And then this one right here, it's not great. It's not great, buddy. And then this one here, let's use that, assuming. And then assuming right here. Well, it's gone too bad, but ooh. Okay. Well, now things are messed up. But hopefully you understand what I mean, because the point is trying to understand the point that I'm trying to bring out here. So we are done with the positive edge trigger flip-flop. Let's do the negative edge trigger flip-flop. Now, again, we are going to use the same D. So we are looking for Q and then the Q bar. Now, Q, so instead of looking at this point, that's the rising edge. This time around, we'll be focused on this edge, right? The falling edge. Now, what's the value of D at that falling edge? What is it? It's a 0, right? So initially, this is a 0. So we maintain 0 on this point until this point. Now, what's the value of D at that point? It's a 1. So we transition from 0 to 1. Perfect. Now, what's the value of Q here? It's a 0, right? So we transition from 1 to 0. Now, and then what's the value of D here? It's a 1. So we transition from 0 to 1 again, and then that way. Now, for the Q bar, should be here. I start from here. Oh, sorry. I messed up. So at this point, it's at 0, right? So instead of remaining at 0 is when we go to 1. Now this point, it transitioned from 0 to 1. So we come down opposite at 1 to 0. Now that point, at this point, it's moving from 1 to 0. So we are now moving up for our case. At this point, it's moving. So we'll move down and then boom. So that's timing diagram for the positive edge trigger and negative edge trigger flip-flop. Now, actually, I wasted a lot of space, but hopefully you get the point. Now from here, we can derive something like a truth table. So where we have, so we have the clock signal, right? And then we have the data signal, and then we have the Q, the output from that. And then we have the Q bar, again, the output of that D flip-flop. Now, when the clock is 0, well, if this one is even a 0 or a 1, the output is undefined, and not undefined actually. It means it stores the previous state. Let's assume the previous state was X because we don't know. So that can be X bar. Now, the moment we make the clock 1 is when things will start to change. Now, if this one was a 0, right, it means Q will follow D. So this will be a 0 and this will be a 1. Now, if the clock again was a 1 and this was a 1, Q will be 1 because it follows D and then becomes that 0. Now, ignoring that section when the clock was at logic 0, let's look at this section when the clock is logic 1. It means just D and Q are the same, right? So for D flip-flop, the output of D flip-flop that comes out from port Q is the same as D. And that's it for the D flip-flop. And the other thing we can say about D flip-flop is that you can use 4 NAND gates or 4 NOR gates to implement the D flip-flop. Now, inside an AND gate, it contains transistors, which are the PMOS, and NMOS. So for one AND gate, you will have 2 PMOS, 2 NMOS, and then we have 1 NMOS and 1 PMOS for the inverter. So in total, you'll have 6 transistors. Now, but you do need 4 NAND gates. That makes 24 transistors for the NAND gate, for the D flip-flop. So with these, with you having known all these, so the takeaways will be, first of all, knowing the frequency and knowing the period, right? The period, and then knowing that Q follows D at the edge of the clock, or at the clock edge. And then make sure you know that truth table. And what are the application of this flip-flop? So you can use these to make counters, and you can also use these to make clock dividers. So you can cascade 2 flip-flops, and you can have, with that you can divide the clock frequency. They are used in registers, and you can, well, they are used also in caches, and specifically the higher level of cache. So you can talk about the L1 cache. You can use flip-flops to implement that, because they will be in a range of maybe 128 KB at a maximum. So you can implement that. But lower level cache like L3, you will need the SRAMs. So those are the application of the D flip-flop that we do have. So next time I'll make a video on the components or the contents of that D flip-flop, which I said they're already NAND and OR gate, and we're gonna see how those works. And NAND and OR gate actually are the combinational logic, which means the output is determined by what you have in the input. There's no clock signal. Well, so that's it about flip-flops, and specifically D flip-flops. There are many types of flip-flops. You have master-slave flip-flop. For the D flip-flop, we have SR flip-flop, we have JK flip-flop, and then we have the T flip-flop. And the most interesting thing is at times you can use D flip-flop to implement T. You can use D flip-flop to implement SR. So it's kind of interesting, but just to know these are memories that's used to store 1 bit of information, which can be 0 or 1. So that's it about flip-flops. I hope you learned something from this, and see you next time.